Hello everyone and welcome back to a brand new video. And in this video, I'll be solving problem C, that is least prefix sum, from the recent Codeforces contest. And I will also try to make a video on problem D, but I cannot promise anything because I recently had my onboarding. So I have a lot of courses and guides to go through. So I don't have that much time on my hands, but I will still try to cover problem D. But still, let's move on to problem C in this video and let's see how we can solve this. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. As you guys know, Newton Schools does this coding contest every month. And this month, the name of the contest is Code Rush X, and the prizes are better than ever before. So you can win prizes up to rupees 10 lakhs. And along with this, you can win placement opportunities in top product companies. So if you guys want to play this for fun or you guys want to play this for placements, that is totally up to you. The contest will be on 28th of January. It will start around 9 p.m. and the contest will be 3 hours long. So there will be ample amount of time for you guys to brainstorm and solve good quality problems. So if you guys want to benchmark yourself or just win some placements, this is a very good opportunity. I will leave a link to this contest in the comments and in the description, so you guys can go and sign up from there and show, or you can flex how good you are at problem solving. So now let's move on to the solution. So in the problem, we have been given two integers, n and m. N is the size of the array, so your n can be up to 2 into 10 to the power 5. And we have m. M is the index in the array, so m goes from 1 up to n. So our array is something like a1, a2, a3, so on up to an. Right, and your elements ai are from minus 10 to the power 9 up to 10 to the power 9. Let's say we build a prefix sum array of this, right? So we build a prefix sum array, something like p1, p2, p3, so on up to pn, right? Where any element pi is just sum of the first I elements of array A, right? So pi is equal to a1 plus a2, so on up to ai. So we build a prefix sum array out of A. Now you can apply some operations on array A, right? In one operation, you can choose any element ai in array A and multiply it with -1. That is, you can change ai to minus of ai, right? That is the operation. Now you want to apply these operation such that your element pm, right? We have this index m. You want to apply these operations such that your element pm is the minimum element among all the prefix sum array values, right? That is, your value pm should be the minimum value among all pi values. Or you can say that there should be no pi value, there should be no pi value that is less than pm, right? There should be no such pi value that is less than pm. And you have to answer the minimum number of operations that are required to achieve this, right? So that is the problem. Answer the minimum number of operations that are required such that your value pm is the minimum value among all pi, right? That is the problem. Now how can we solve this? So let's move on to the observations and try to solve this. Right. So the very first observation that we need is how does an operation affect array P, right? We know what operation does on array A, but we need to check how will it change array P. So first of all, let's try to see what operation does on array P. So we have our array A1, A2, A3, so on up to an, right? And we have a prefix sum. This is p1, p2, p3, p4, so on up to pn. So initially my p1 was a1, my p2 was a1 plus a2, my p3 was a1 plus a2 plus a3, and so on. Now let's say I apply an operation on A3. So my A3 will change to minus of A3, right? Then my new P array becomes, this will be my new P array. It will become A1, A1 plus A2. It will become A1 plus A2 minus A3. Similarly, this will become A1 plus A2 minus A3 plus A4, right? So if you see the difference here, the first two elements won't change, right? But if you see P3 before and P3 after, there is a difference of minus 2 times A3, right? Let's call this P3 dash. So like if you find P3 dash minus P3, it will come out to be minus 2 times A3. That is, your like element has decreased by 2 times A3. Similarly, if you check P4 dash minus P4, you will get that it is also a difference of minus 2 times A3. So like your entire suffix will be reduced by minus 2 times A3. So you can say that in general, if we have A1, A2, A3, so on up to An, if we have some element Ai here, if we apply an operation on element Ai, then in array P, we have P1, P2, P3, P4, so on up to Pi, so on up to Pn. Then in array P, all the entire suffix from index I up to index n will be reduced by minus 2 times Ai, right? So that is the operation in your array P. So now we have to use this operation to make your element Pm the minimum. So now let's see how we can achieve this. So now let's move on to the optimal operations. Observation 2, optimal operations. So I will break this problem into two parts. First part is on the left side of Pm and the second part is on the right side of Pm, right? So let's say first we talk about on the left side of index m. That is when your index I is less than up to m. So we have something like this. We have P1, P2, P3, P4, so on up to Pm, right? So we can like place a pointer on Pm, right? Initially we are here and we'll store the value of Pm. Let's say value of Pm is some value x, right? So we have this value x. So then we can start moving to the left, right? Let's say we move to the left, we get P of m minus 1. We will compare Pm minus 1 and x. If my value of Pm minus 1, right? If my value of Pm minus 1 is greater than x, then I don't have to worry about this, right? If my value of Pm minus 1 is greater than or equal to x, then I don't have to worry about this, right? This is okay because our Pm is still the minimum. So like I will store this value into you can say a max heap, right? So I will keep a max heap and I will store this value into my max heap, right? So I will store this into my max heap. Then I will move on to Pm minus 2. I will again check the same thing. If my Pm minus 2 is greater than or equal to x or not. If it is, then it's okay. And I will also insert this into my max heap. Then I will move on to Pm minus 3. Then let's say that your value of Pm minus 3 is less than x. That is, your Pm minus 3 is less than Pm. So we have to do something here, right? Because like your value of Pm is not the smallest anymore. So you have to take some action here. But like where should we apply the operation on this? Where should we apply the operation? So if you think about this, let's break it into two parts as well, right? So we have P1, P2, P3, so on up to Pm minus 3. Sorry, we have Pm minus 4, let's say, Pm minus 3, Pm minus 2, Pm minus 1, and we have Pm, right? Let's say we break the problem into two parts. Let's say the first part is this one, right? From P1 up to Pm minus 3. And second part is from Pm minus 2 up to Pm. So what happens if we apply operation in the first part, right? Let's call this part 1. What happens if we apply the operation in part 1, right? So let's say we choose some random element Pi here and we apply operation on that. So in that, entire suffix will be reduced by minus 2 times Ai. So your value of Pm minus 3 will become Pm minus 3 minus 2 times Ai, and your value of Pm it will also become pm minus 2 times ai, right? But initially we know that value of pm minus 3 is less than pm. So like if we subtract minus 2 ai from both sides, we get pm minus 3 minus 2 times ai is still less than pm minus 2 times ai, right? So you can see that the operation was basically useless. Like before the operation, this was before the operation, the value of pm minus 3 was less than pm, and even after applying the operation, value of pm minus 3 is still less than pm. So like the operation was useless. So like it is not useful to apply operation in part 1, right? It is not useful to apply operation in part 1. So like we can ignore part 1. That's why we are keeping a max heap here, right? We are iterating from the left and we are keeping a max heap. So we only care about values that are in part 2. Because like if you apply operation on part 1, it will be useless. So we don't like care about values of part 1. Part 1 is useless to us. So that's why we are keeping a max heap and only storing the values of part 2. So now we know we have to apply an operation in part 2. But like which element do you choose? So we want to make pm less than pm minus 3, right? So let's say we choose some element pi. Let's say we choose some element pi in part 2, right? Then your pm minus 3 will not change, but your pm will change, right? Your pm minus 3 will stay pm minus 3, but your pm will change to pm minus 2 times ai, right? Because now we are choosing some index I in part 2, and like your pm minus 3 will not be affected now. So now you need to make, that is pm minus 2 times ai should be less than pm minus 3, right? That is your goal. So like which value of ai should you choose? Obviously you want to like make pm less than pm minus 3, so you should choose the largest value, right? Because your goal is to make pm smaller. So why will you choose a suboptimal value? Like if you get the chance, you should choose the largest value in part 2, right? So choose the largest value in part 2, right? Largest ai value in part 2 and reduce pm. So like the larger value you choose, the larger pm will, like the faster pm will get smaller, and like faster it will become the smallest element, right? So it is always optimal to choose the largest value of ai to like do minimum number of operations and make pm smaller faster. So like you are keeping a max heap, so you can just query your max heap and find the largest element, right? So your algorithm is, or your optimal approach is, just query the max heap to find the largest ai value in part 2 and update your pm value, right? So keep doing this until you reach the left end, and that will be your approach for the left side. So now let's move to the second part. Let's see how the algorithm will change when you move on to the right side of him, right? So let's move to the second part of the problem. For now we have taken care of all the indexes that were on the left side of him, but now let's see what happens on the right side of him, right? So now we have pm, so you can say your index like I is greater than m. So we have pm plus 1, we have pm plus 2, so on up to pn, right? So again we'll do the same thing. We'll start from here and we'll again like keep iterating to the right side, right? This is pm, we'll keep iterating to the right side, right? Let's say your pm plus 1 is greater than equal to pm, right? Then it's okay. Then here I will keep a min heap. Here I will keep a min heap. Why not a max heap? Like I will explain this later in the solution, but let's assume you're keeping a min heap here, right? So I will say let's say your pm plus 1 is greater than equal to pm. Then in this case I will push like my pm plus 1 into my min heap, because it's okay, right? Because I don't have to do anything for pm plus 1. Similarly, let's check pm plus 2. Like if pm plus 2 is greater than equal to pm, then it's okay. Then I will also push this into my min heap. Similarly, let's check for pm plus 3. And let's assume that your pm plus 3 is less than pm. Your pm plus 3 is less than pm. So now we have to do something here, right? Now we have to do something here. So what can you do here? So let's again break the problem into two parts, right? Let's break the problem into two parts. So we have PM, PM plus 1, PM plus 2, so on up to PM plus 3, and then we have PM plus 4, so on up to PN, right? Again, let's break the indexes into two parts. Let's say this is part 1 and let's say this is part 2, right? So we know that your PM plus 3 is less than PM. So you can see that if you apply operation on part 2, like if we apply operation on part 2, it will not change PM plus 3 and it will not change PM, right? So our inequality will not change. So applying an operation in part 2 is not optimal, right? Applying an operation in part 2 is useless. So we can ignore part 2 for now. So now you have to choose some value in part 1 and apply operation on that, right? So let's say you choose some index pi and apply operation on that in part 1. So in this case, your value of PM plus 3 will reduce, but your value of PM will not reduce, right? Your value of PM will not reduce, but your value of PM plus 3 will reduce. So let's say you choose some value AI. So your value of PM plus 3 becomes PM plus 3 minus 2i, and your value of PM will remain the same. So now your PM has to be less than PM plus 3 minus 2i. So like to make this happen, your AI should be negative. Your AI should be negative, right? Because if it's positive, if your AI is positive, your value of PM plus 3 will reduce even further, and we don't want that, right? So in this case, you will not choose the largest AI. In this case, you will choose the smallest AI, right? Because we want our value of PM plus 3 to increase. So you will choose your like most negative AI, and it will increase the value of PM plus 3, and like your PM will become smaller, right? So in this case, we will choose the smallest value, or you can say the most negative value, such that it will increase the value of PM plus 3, because when you like do a negative element, this will become positive, and like it will increase the value of PM plus 3, and our PM will become smaller, right? So that's why we are keeping a min heap here. So that is the entire solution and how we can solve this. So like if I write the pseudocode for this, pseudocode will look something like this. So let's say you set your value x, or you can say your value current, as equal to P of M. Then we can start iterating from the left side, right? So let's say for index I going from M up to index 1, that is we iterate on the left side. We will check while our value of Pi is less than current, we have to apply some operation on this, right? So we will query our max heap, right? So query this, and let's say we get some value y. So you can update your current value, your current will change. Your current is equal to current minus 2 times y, right? And then you will update your answer, because we are applying an operation here. So you need to update your answer here as well. After you're done with this, you can push your element AI into the max heap, right? So max heap, you can push your element AI. That is, we can use this element for further operations now, right? So that is the entire algorithm for the left side. Now for the right side, you will again set your current equal to P of M. Now why are we doing this? Because applying operation on the right side, like they did not affect the relative difference on the right side, right? What I mean by that is, if we have P1, P2, P3, so on up to PM, let's say so on up to PN. So let's say this is the right side, right? So let's say before the operations, we find the value of Pi minus PM. And after you apply operation on the left side, right? After you apply operation on the left side, right, this difference will not change. So after and before Pi minus PM, it will remain same. So no matter whatever operations you apply on the left side, if there is some element Pi on the right side, the relative difference between Pi and PM will not change before and after the operation, right? So like in respect to the right side, we can again set our current equal to P of M. It should not matter, right? So we reset our current value equal to P of M. Then we start iterating on the right side. So for index I going from M plus 1 to N, in this case we'll keep a min heap, and in this case we will first push our element. We will do min heap push ai. Now why are we pushing the element first in min heap? Like in max heap we were pushing the element after, right? But in this we are first pushing the element into min heap. For that you can see the diagram above, right? In that case, like in the max heap case, our pm minus 3 was lying in part 1, right? It was lying in part 1, and part 1 was useless, right? So we could not have used pm minus 3. That's why we were pushing pm minus 3 after we were done applying the operations. But if you see in the second part, my index pm plus 3, where is it? Yeah, my index pm plus 3 is lying in part 1 here, right? And in this case, part 1 is useful, right? So I can use index pm plus 3 itself, right? So I have to consider index pm plus 3. So I will first push this into min heap because this index is usable. So that's why I will first push my index ai or element ai into the min heap. Then I will do the same thing. While my p of I is less than current value, I will query the min heap, right? Query the min heap. Let's say I get some value y again. So I will do pm minus 2 times ai, right? But this is the same thing as doing pm plus 2 times ai, right? Because if pm is less than p minus 2i, then I can just shift this minus 2 times ai to the left side, and this becomes pm plus 2i. So subtracting 2i from element on the right side is equivalent to adding that element 2 times to the pm value, right? So I can just do current is equal to current plus 2 times y, right? This is equivalent to this case, and I can update my answer. So answer plus plus, and in the end you can just print out your answer. So cout answer and L. That will be your entire code, or you can say pseudocode for this, how you can implement this. So if you guys want to see the code for this, here is the code. Sorry for that. Yeah, so here's the code. So I will keep two variables, n and m. I will create my array a and my sum array, prefix sum array. So then I will iterate on the left side. So this is my current variable current is equal to prefix of m. I will keep a max heap and I will iterate on the left side. So while my prefix of I is less than current, I will pop the top element. I will subtract it from my current element and update my operations. And then I will push the element into max heap. Similarly, I will update my current value as equal to pref of m, right? Then I will keep a min heap. I will start from m plus 1 and go up to n. I will first push the element into min heap and then check if my pref of I is less than current or not. If it is, I will query the smallest element and add it to current. This is then just answer plus plus, and in the end I can just print out the answer. So that is the entire code, and if you guys have any doubts, feel free to ask in the comments or join my Discord server. I'll be more than happy to answer your doubts there, and I will see you guys in the next one. Bye bye.